So let's switch this a bit. This is the last time I think that I really need to say this, and so I won't. Your notes are not helpful to you, right? That should be clear. Those of you who didn't get 5 meters per second, or even are sitting and staring at blank things, you don't have notes that help you. You need notes that help you. What do you think you should write down here? So I'm going to say things. If you didn't think to do this, that's something you should write down. And don't write down what you see put on the board. Write down a note, a sentence that says, I should start here and begin there. That would probably be helpful. I'm going to tell you to start with a quick sketch. I think for a problem like this, there's so many things, a quick sketch tends to help. So let's start with a quick sketch. This is an object rolling off of a table. So I'm going to kind of start with a table-like sketch. On my sketch, I'm going to label what happened. A ball is being pushed. How fast is the ball being pushed? We don't know. I guess I'll put a question mark there. It's a good place to start. Now, the problem told me more things. Can you name something else the problem told me? Yes, sir. The bucket is 2 meters away. I'm going to put a little X there because that's where it has to land. Yes, sir. Perfect. The table was 0.8 meters high. Yes, sir. The ball will be in free fall, and it's going to be pulled down by gravity. That's a true statement. I don't know that I said that, but I did say I'm going to roll it off the edge of the table. I'd argue that this is the information we have. So once you've kind of identified the problem, what it is you need to answer and what parameters you've been given, I would organize the details. I suggested an organizational structure, a chart. So the next thing I would have you do is draw a chart to help you organize your information. Is that in your notes? A bit of information to tell you how to get organized. I make my chart with a vertical side and a horizontal side. And my vertical side has 5 pieces of information on it. That shouldn't be a surprise. It's your motion variables. So delta y, vy initial, vy final, acceleration and time. And my horizontal side experiences no acceleration, so there are 3 motion variables, delta x, vx, and t. Again, what are you putting in your notes? If you just wrote those things down, that's not enough. You need to tell yourself to organize your details. Recognize the problem is broken up into 2 parts, a horizontal part and a vertical part. These are the details you need. You need instructions on what to do. If all you do is go back and look at your notes and you see a complete problem, you don't even know where to begin. I'm telling you where to begin, a picture and a chart. That's where you should begin. I will help you understand that your goal here is all about time. You need to find how long the object is in the air. That's going to solve your problem one way or the other. So before you get started on your chart, I think it a good idea to identify what direction will be positive. I'm making downwards positive and to the right positive. And that's because many of these variables are vectors and knowing their direction is helpful. Did you put that down as a step? Check direction, be consistent, identify what direction is positive. Right now that's easy, but it will be harder soon. So at this point, I'm going to put in here the things that I know about the problem. Now, I'm going to name each variable and what it is. I know it seems silly because I watch what you guys write down. So I know that you don't write the things down that I think you should. But you don't want me to be that teacher who tells you what to write down. And I'm not going to PowerPoint this for you. You need to direct your learning. This is a college class. You guys are doing all those things. I'm not talking to you, and I hate that you guys get lumped in with that. But there was a lot of people who I just walked around and saw had no start. Look, delta y is going to be the change in height of the object. Where did it end up compared to where did it start? This object started on the table and ends on the floor. It is 0.8 meters below where it started. The initial y velocity is how fast it's going up or down at the start of the problem. Now, that is important because you'll put the wrong thing here. I watch students do it all the time. But for this problem, it's 0. There's no ramp there. When that ball leaves the table, the moment it's in the air, it has no up or down velocity. I don't know how fast it's going when it reaches the ground. I wasn't told that. Acceleration, that's whatever's causing its velocity to change. It only changes in one dimension, and that's gravity in this case. And for most projectiles, it'll be gravity. 10 meters per second squared. I don't know how long it's in the air. Although I bet it's in the air for the same amount of time as yesterday, because everything about the left side of this problem is the same. So you really only had half a problem to do. I didn't tell you that, but you did. Now, we haven't identified everything yet. There's still more information that was presented in the problem, and we haven't slotted it someplace. The 2 meters. It's how far the object travels sideways, sometimes called the range of the problem. Well, we've been working on the vertical side. I think it's time to switch to the horizontal side. Sideways means horizontal. So, that'll be this one, 2 meters. Now, the problem presents us with a question mark. This is where the question mark goes. It's probably a good idea to figure out where that question mark goes. All right, that's it. That's the whole problem in a nutshell. You've identified all the information. Now, these problems are all the same in that at some point or another, you need enough information to figure out time. That means either 2 pieces on the right side or 3 pieces on the left side. I have 3 pieces on the left side. I'm going to use one of my motion equations. Yep, I know. You need those motion equations. Look, your tests are out here in the front of the classroom. Perhaps on your way, if you didn't rip your note card off of your test and you're saying you lost yours or don't have yours, it's probably stapled to your test still. Just grab it. You can have your whole test if it's been graded. I'm going to choose a relationship here that has all these things in it. I mean, I'd also probably assume that this is in your notes somewhere, but I can't assume that much, I guess. At this point, I'm kind of redoing a problem we did yesterday, so I'm not talking very much about it. Arithmetic is so particularly boring, I really don't care about it, but you probably do. Do your arithmetic. Once you have figured out the time applies in both places. Do you now have enough information to figure out how fast the object is traveling? I believe you do. It's not a motion equation over here. It's just delta x equals vx times t. It's not accelerating. It's not accelerating. So the object's displacement equals how fast it's going times the time. We have displacement and we have time. So 5 meters per second. Not terrible, I don't think. All right. I assume I am still going to use this chart, which some of you refuse to use. Trust me, you guys who are struggling, giving you a place to hang all your numbers, consider, for just the time being, do it my way. And then when you're no longer struggling, do it your own way. There's nothing more disheartening than walking around the room, asking people if they're doing okay, hearing them say yes, and looking at a blank piece of paper in front of them. It hurts my heart. Looking at all of this, can you assemble your chart? I mean, I know I can do it. You should try it first. You should always be a little bit ahead of me if you're doing okay. Assemble your chart with what's been given here. You've been given all the things you need to do this problem. So take a minute. Assemble the chart, please. I'm going to make upwards positive this time, and to the right positive. This should take you 30 seconds to assemble your chart.
That's in 40 degrees.
Yep. All right, that's about 60 seconds. 20 sine 40 will be the initial y velocity, and it will be positive. The acceleration is going to be 10 meters per second squared. And it will be negative. (20 cosine 40 degrees will be the horizontal velocity. And this is a type 2 problem. So delta y is 0. That's it. That's all the information that's given. You're trying to figure out where the ball lands. Now, this problem is identical to the one you just did. Find the time and use it on both places. You have enough information here to find the time. That's 3 pieces. You should use it over here to find out where it lands. This time, I think I should pick on one of you. It tends to heighten the level of concern. And having walked the room twice, I know who should be concerned. You have a lot of people around you who can do this problem. Talk to them. All right, so if you made it to the first part of this problem, then you know you're going to use 0 equals 1/2 a t squared plus, is it 12.8 t? Is that right? Now, what's that? 12.9? I've seen a few folks who have some difficulty with the arithmetic here, and some people who did just way more work than they needed to. This only has the 2 terms there. You don't use, although you could use the quadratic formula to get the time, you really don't need to. You can factor out a t. And just set 1 equal to 0. But that's not the one you care about. You care about the other one. When we're asked when the ball is on the ground, so it's going to give you 2 times. The ball was on the ground at time 0. It's going to be on the ground a little bit later, too. So it'll be on the ground at whatever 12.9 divided by 5 is. Right? You said each term equal to 0. So I don't think I need the t equals 0 term. But what I'm finding is that some people are intrigued by what I did to get the answer here. You need help, okay? You need help. You need practice. You need to remind yourself of your algebra rules. And I'm willing to help you, but for those of you who need that help, you need to ask for it. I hate to see you flounder on this. There's a lot of math here at the beginning of the year. It won't always be like this, but we're always going to be supported by math the whole year. So if you're having difficulty with this, please come get some help. Either way, that gives me a time of, I don't even know what the time is. So 2.6, but keep more decimal places. And that makes this 2.6 seconds here. This is still more arithmetic. Delta x equals 20 cosine 40 degrees times 2.6 seconds. This is probably going to be somewhere around, 40 meters. It's 39 point something meters. To land a marble in a bucket. The bucket is 3.5 meters away from the edge of the table. The table, just like yesterday, is your desktop, which is 0.8 meters high. How fast do I have to roll the marble in order to make it in the bucket that's 3.5 meters away? By giving you the table the same as yesterday, I left almost all the parameters the same as yesterday. Now, if your notes aren't helping you, you need to change them. I know you're tired of hearing me say this. I know first period was definitely tired of hearing me say this, but if your notes are not useful, why take them? Are they telling you what to do? Are they telling you the things that I'm telling you to do? I gave you a framework, a place to start, and a set of instructions. And you have the capacity to write this down. You're never going to get from me, a handout that has this kind of stuff on. I'm expecting you guys to put this together on your own. This is college. So I would start by identifying the problem. There's clearly a problem here. How fast does the ball have to go? Then I gave you a place to begin. I said it would be helpful if you had a way to organize the data. So I recommended a simple chart that had 2 columns in it. And I said write vertical on one and horizontal on the other. The object's going to experience acceleration in the vertical dimension, so that's going to have to be the whole range of motion variables. But the horizontal experiences no acceleration, so fewer variables. Now, you've been given information to use here. You have to identify where it's going to go. I don't think it's terribly tough, but I've watched kids do this a long time. And you guys really don't think about what these things are. I'm going to start in the upper left-hand corner and just ask questions. Delta y represents the vertical displacement. Did the object land higher than it started or lower than it started? If so, a number's going to go there. I'm going to put 0.8 meters there. That's how far below where it started the object lands. I'm encouraging you to say, I'm not saying all this out loud for a reason, for my own health. That's the question I ask myself when I go through this chart. The initial y velocity is how fast the object's traveling up or down at the start of the problem. This object is launched at an angle of 0 degrees, which means it's not traveling up or down at the start of the problem. The next one tells me how fast it's traveling vertically when it hits the ground. That'd be how fast it's going here, and only the downward portion of it. I don't know what that is. It wasn't given to me, and I haven't found it. I have to leave it blank. But I do know that it is accelerated by gravity. Now, there's a number I haven't used yet, and that's fine. I still have a whole column I haven't talked about, where delta x is the range. It's where it lands horizontally. It's the distance it travels horizontally. They tell me that, 3.5 meters. And that's the extent of what I've been given. It's up to me to recognize this is what they want me to find. How fast did I push the marble horizontally so that it will land there? Now look, it's a lot. Did you write anything down? I watched your pencils. So now I know. So when you don't get the next one and you wonder where to start, I just told you where to start. I would always draw a picture first. And on that picture, I would identify what you're going to call positive. I think that that's an important thing to do. I draw pictures up here a lot. Are you drawing pictures? I look at your notes, I know. But there's a lot of people who don't even bother to do this, and I don't understand why. Especially when you walk by and I say, what's the answer? And you say, I don't know. No matter what comes out of your mouth after that, if you haven't organized yourself, you sound a little ridiculous. Maybe even a little obstinate. So I'm going to choose to make, so I've made upwards positive, those two have to be negative. Yesterday I made downwards positive, today I'm making upwards positive. Just switching it up, making sure you're paying attention. But yesterday we had the same height table, so most of you realized that you got the same answer for time. You didn't really have to work that out. Everything over here was the same. So it's still going to be 0.4 seconds. But I had people who couldn't get 0.4 seconds. Having that zero makes this easier, though, isn't it? It's nice having a zero in a problem. So that's why I'm able to use that zero effectively. Once I find the time, that goes in two places. The time it takes to go vertically is the same as the time it takes to go horizontal. Now, finding out the launch velocity is pretty straightforward. It's delta x equals vx times t. You just need the two pieces over there to figure it out. So Vx is going to be 8.75, I think, meters per second. It's a very straightforward question. And it's part one of your lab practicum. In your lab practicum, I'm going to set up that projectile launcher. And are still the same. All of these problems are done the same way. A type 2 question is identified by the fact that the object itself is now launched at an angle, which makes a difference, clearly. So it will have some launch angle and some launch velocity. That's okay. Let me see if I can do better. There we go. One of the major differences is that in a type 2 problem, we're going to launch and land at the same height. We're going to try and find a way to work a zero into the problem, because we know zeros make the problem easier. So I call a type 2 problem a problem in which the object launches and lands at the same height. You throwing a baseball to a friend, probably a type 2 problem. A punter, maybe not a punter. A punter if the guy catches the ball, but a place kicker if they kick it off the ground and it lands on the ground. A golfer if the course is not have a change in height. And these would all be examples of what I feel is a type 2 problem. Not going to try and trick you. You'll know. The issue, though, is you're not usually given the components of your velocity. You're given a launch velocity and an angle. So under the circumstance of a type 2 problem, you need to realize that you'll have to do some trig. I don't want to do the trig for you anymore. And I gotta be honest, first period really took it out of me. So you should be able to break this up into its component vectors. You'll need a horizontal component and a vertical component. Now, I'm making the grand assumption that your angle is measured relative to the horizontal, and it almost always is. But don't be complacent. Understand that what I'm about to do is based on it being measured from the horizontal, and if it's not, you will have to change. And if I want to mess with you, I just measure the angle from the vertical instead and see if you're paying attention. But I find that most of this stuff is hard enough. I don't have to find ways to mess with you. Even the honest problems trick you. So constructing a triangle around the angle, just like we talked about last week, I'll label this Vx and this Vy initial. And I'll recognize that this is the opposite side, this is the adjacent side, and this is the hypotenuse. You should do sine and cosine to figure out what each of these components are. I'm kind of done doing that though. So this one is V naught cosine theta, and this one is V naught sine theta. And you can probably count on this as long as the angle is measured relative to the horizontal. This will have to be true. The angle's not measured from the horizontal, you're going to have to do better. That should be enough for you to figure out a straightforward type 2 problem. Like a kicker kicks the ball at 20 meters per second and an angle of 40 degrees. Where does the ball land along the ground? I'll give you 2 minutes. I think that should be sufficient. Okay, launch the ball 20 meters per second at an angle of 40 degrees. I would like to know where along the ground the ball lands. Walking around the room, we have a variety of skill sets here. So just a reminder, these steps that I'm giving you aren't arbitrary, and they're all there for a reason. So when I'm suggesting you do these things, it's not because, I have this grand vision of how I want it done. It's because these are all the things that have to happen for a successful completion of the problem. The object lands at the same height it was launched. That means delta y is 0. It's launched upwards, but we don't know the exact velocity. We know it's 20 meters per second times the sine of 40 degrees. So 20 times 40 sine gives me 12.9. I don't know how fast it's going when it reaches the ground, but I know the acceleration's 10 meters per second squared. And the horizontal velocity, 20 times 40 cosine, gives me 15.3 meters per second. So I've taken the information I was given and I tried to apply it to all the things that are here. That's huge. There's a lot of data to consider here. And we're just scratching the surface right now. But the next part, a lot of you forget to do. I'm going to make up positive into the right positive. Otherwise, you might not think it's a big deal until you try to take the square root of a negative number or something weird happens. So decide. That's going to make this one negative. Even here, though, people stumbled. You want a relationship that has these 4 things in it and not this one. That's what you want. That one will probably do it. Now, this one's a simplification because it worked a 0 into the problem. You can probably see a future where without that 0, this problem is a little bit more difficult. But some of you reached this point and still have some struggles. This is the algebra. It's arithmetic. I don't want to stand on this very long. If you can't do the arithmetic, you will run into more difficulty in the future, so we need to practice. But it's not the end-all of this class. So for you guys who struggle there, we'll handle a little time. We'll work on it. I like to do math the way we're supposed to, which is to factor out a t. Some of you just divided by t. I don't care. We know that the one number t equals 0 is not necessary. But some of you don't understand why I'm saying that. I'm saying that because if I factor out a t, my relationship looks like this. And I can set this t equal to 0 and all of this equal to 0. Which gives me that my time is about 2.6 seconds. That means this is 2.6 seconds. All right? Look, that's the bell.